go and figure out what's the normal vector at this point. But that means I need to know what u and v are, right? So I have to now figure out what's u and what's v that get me to this point on the original curve. Right? As I vary u and v around, I start drawing these things, right? I draw the whole surface. What does u and v have to be to get me to here? So where do you want to start? Yeah, I know that this right here has to turn into that, right? I know that cosine of u has to be root 2 over 2. Can you tell me what u has to be then? Where's cosine of u root 2 over 2? Pi over 4? U must be pi over 4. Anywhere else? 3 pi over 4? No, wait, not 3 pi over 4. It's over in the fourth quadrant, isn't it? Which is outside of my, right? Cosine is the x-coordinate on the unit circle. That's only positive in the first and fourth quadrants. So pi over 4 is the only solution that lives in here. Okay, so we've nailed down what u is, right? Okay, let's look at this one right here. This has to be equal to that. So I must have that sine u times sine v must be 0. But I know what u is, right? U is pi over 4. What's sine of pi over 4? This is root 2 over 2. Sine v must be 0. Divide both sides out. You have sine of v must be 0. Where's sine 0? 0 and pi and 2 pi, right? So I have a couple of different options here. V could be 0, pi, or, yeah, I'll say or 2 pi. Do you agree? That's not good enough. So we should be able to get it from this last one. How about this last one? Cosine v sine u must be root 2 over 2. We know what u is, right? U is pi over 4. Then this would be sine of pi over 4, which is root 2 over 2. So cosine v times root 2 over 2 must be root 2 over 2, which means cosine of v must be what? 1. Where's cosine 1? 0 and 2 pi? Okay, 0 and 2 pi. Well, if we plug in 0 or 2 pi, we're going to get the same point on the surface, right? See, over here it was 0, 2 pi, or pi, but pi could not be because it wouldn't satisfy the first one. What happens is if you keep drawing this, it's going to keep drawing the same sphere over and over. If I open this restriction up to like 0 to 4 pi, it's going to draw two spheres, one on top of the other one. So we have one point that's being overlapped here. So we can use 0 or 2 pi. It's going to give us the same result here for our normal vector. So what do y'all want to use, 0 or 2 pi? Use 0? Okay. All right, let's get this. The normal vector at this, u was pi over 4 and v was 0. I'll just put it up here. U was pi over 4, v was 0. And now we get the normal vector. The normal vector is, plugging in, what is this? U is pi over 4. So sine of pi over 4, root 2 over 2 squared, 2 over 4, which is half. So we have 1/2 times what's cosine of v. Cosine of 0 is 1, and then, okay, keep going. What's sine of 0? 0, that's all gone. What's cosine of u? What's cosine of pi over 4? Root 2 over 2. What's sine of pi over 4? Root 2 over 2. So root 2 over 2 times root 2 over 2? 1/2 again. There's our normal vector. Questions? You sure?
Yeah.
You got it?
I was just thinking, what if we had picked 2 pi and then I see that the middle one would be 0?
It would still be 0. Yeah, it wouldn't matter. All right, so the final answer for the equation of the plane that's tangent to that sphere at root 2 over 2, 0, root 2 over 2, at that point, is ABC, right? That's ABC? So A, x minus root 2 over 2, plus B, which is 0, times y minus 0, so it's not there, plus 1/2 z minus root 2 over 2 equals 0. There it is. Of course, you could clean it up. You can multiply both sides by 2, however you want. That's the equation of the plane. If we graph this plane, it should touch that sphere. At that point, it should be tangent to the sphere. Questions? What's remarkable about this is we should be able to do this for any surface, so long as you can cross the partials, right? If you can cross the partials, you're in business. Well, and if you can come up with the parametric representation of the surface, then you should be able to. Now, I think we're going to extend on this idea now a little bit more. We're going to talk now about surface area. We've been able to draw surfaces, right? Using this R of UV, we can draw a surface, three-dimensional space. We know that we can pick a point on it and we can find a tangent plane. But what if you want to know the area of a surface? Is there a way to do this? And we can, and here's the formula. It is the double integral over the region D, where D is going to be your restrictions on U and V. Now remember, you draw the surface with U and V, and you put restrictions on U and V. D is the domain restrictions on U and V. If you take a double integral over that of this dA. Now let me try and help you see where this comes from. Let's imagine we want to find the surface area of that particular surface, which in this case I made it a sphere so it's easy to see. If I wanted to find the surface area of this, I know I could draw it by changing my U and V, right? But let's just see, what would it take to figure out the area of that little infinitesimal little patch? Right? This is just a little infinitesimal patch on here. And I'll want to add up all the patches. Right? If you add up all the patches, you get the total surface area. So one way I could do this is I could come down here like this, right? That's the tangent plane. Agreed? These two vectors are the whats? Those are your partials, right? Those are your partials. The area of this plane right here is the area of a parallelogram, isn't it? And do you remember the formula for the area of a parallelogram spanned by two vectors? It's the magnitude, right? The magnitude of the cross product. So you got to remember back from earlier classes that the magnitude of the cross products of two vectors is the area of the parallelogram. Refer to old notes. Two vectors, and you want to know the area of this. That's the cross product of the two vectors. So does it make sense to you that in order to find the surface area of this thing, what I should do is somehow scale that scale that, I went a little too small. Scale that thing down. So in other words, instead of taking this entire vector, which let's say is r, the partial with respect to u, and let's say this one's the partial with respect to v, instead of taking the whole thing, maybe I need to scale it by something to make it shorter. How about we scale it by, I don't know, something like infinitesimal, like du, the little differential, and then do this one like dv, something like that. Then what we should get is an infinitesimal patch like this, and if we add them all up, then we would get the surface area. That's the idea behind this. And what would happen if you took this and you crossed it with this, the constants would pop out, and you would have du dv times each other. And guess what du dv is? It's dA, right? Because du dv, it doesn't matter which way I do it. That's what's basically happening here. Pretty awesome. I want us to find the surface area, and I want to change this. I don't want the unit sphere. That's too boring. Let's find the surface area of the sphere, radius. Let's go, so we don't confuse it with other r's, radius A. Now, if you look this up in a book, what's the formula for the radius, the surface area of a sphere radius r? If you don't know it, don't worry about it. 4 pi r squared is the formula. The area of a sphere radius r is 4 pi r squared. So here's what our goal is. When we're done, we should get an answer of 4 pi a squared, right? That's what we should get if it matches up what you'd find in a book. All right, let's do it. You ready? Okay. I need to be able to draw the surface first. So how about we do it with this? R of uv equals, let's use the same thing we used just a second ago, except it's not radius 1, right? It's radius A. So I'm going to go A, what was it, cosine V sine U? Is that what I did? And then A sine V sine U, or sine U sine V. Then the last one, A cosine U. Are we on the same page? My U's between 0 and pi. My V's between 0 and 2 pi. We still good? If I'm going to use this formula, which is double integral over d of RU crossed RV dA, then I'm going to need to know some restrictions on d. Do I know the restrictions for d? Yes, here they are. So I'm good with the limits of integration. I'm going to have to figure out what the cross product of the partial derivatives is, and then take its magnitude. This is the part that's going to suck. All right, let's be careful and let's carefully go through this. What's the partial of r with respect to u? And now we have an a in here, so do you think we're going to get the same exact thing? Yeah, except what's the only difference? Think we're just going to have an a in there? Is it going to be an a squared? Uh-oh. Let's do this first partial. With respect to u, it would be a cosine v cosine u, a sine v cosine u, and then negative a sine u. Right? That's what that first one would be. Partial with respect to v would be negative a sine v sine u, a cosine v sine u, and 0, right? Cross them. What do we actually have in there? when we do our little crosses here. We get 0 there, and then we get a squared cosine v sine squared u. What's the next one? Cover this one. Will it be minus or plus? It's a plus, remember? Because it was that weird minus, but it was the middle one. So we'll get a squared sine v sine squared u. And then the last one's the ugly one. A squared cosine squared v cosine u sine u minus a squared, is it minus? Plus. Plus, sorry. Plus sine squared v cosine u sine u. So very similar to what we had, right? We weren't sure if it was going to be an a in there or an a squared, but it's a squared. Do you see that? This one becomes, just for the sake of time, this becomes, we can pull out an a squared cosine u sine u and then get Pythagorean. So we should get a squared cosine u sine u. So if you look back at the previous problem that we did, when we did this cross on the unit sphere, we just, all the a's, a squareds, they were all, a was 1, so we didn't see them. Okay, next. Magnitude. The magnitude of a vector is the square root of the square of each of the components. So we have to square each of these components, add them together, take the square root. And that may sound bad, but it's not going to be that bad. In fact, it's going to be great when it's all said and done. Things are going to go away. The magnitude of this will be square root of, okay, when I square this, I get a to the 4th cosine squared v sine to the 4th u. When I square this, I get plus a to the 4th sine squared v sine to the 4th u. And then when I square this, I get plus a to the 4th cosine squared u sine squared u. Anyone see it? Where's the Pythagorean? Yeah, why don't we do this? Why don't we pull an a to the 4th out of everything and take it out of the root? An a to the 4th on the inside comes out as an a squared on the outside. Then, I'm ignoring those now, okay? On these two, I have sine to the 4th u, sine to the 4th u. Just pull that out of those two only. And I'll have sine to the 4th u cosine squared v plus sine squared v. And then over here I have plus cosine squared u sine squared u. Right? Yes. Which this turns into a 1. Pull out so with what's left, right, that's gone, pull out a sine squared u. You'd be left with sine squared u. So I'm pulling the sine squared out from this and from this. I'll be left with the sine squared here and left with the cosine squared here, which again becomes a 1, which gives me a squared square root of sine squared u, which is going to be a squared sine u. I don't need to put absolute value because u is between 0 and pi. Sine is always going to be, 0 to pi. Yeah, so it's always positive, so we're good. We don't need to worry about that. All right, that's it. Any questions on where I got any of that? Now we just integrate, right? Double integral. All right. So we're going to go double integral over d of a squared. So I'm going to pull that out because that's a constant, sine u dA, which in this case I know my restrictions, and they're both constants. So 0 to 2 pi, 0 to pi, sine u, I have to go d what here? With the order I chose here. d u dv. What's the antiderivative of sine of u with respect to u? Negative cosine of u, evaluated 0 and pi, dv. I know I'm going quick, but this should be trivial stuff at this point. Plug in pi, you get cosine of pi is -1, but then minus, so it's a 1. Minus, now plug in 0, cosine of 0 is 1, but minus, which is -1, but you're subtracting it, right? So that's really a 2, right? So you've got a 2 comes out 2a squared. It's looking promising, isn't it? Remember what we were trying to get to? Right? That's encouraging. I'm integrating, I pulled the 2 out, I pulled the a squared's already out there. This is just really like a 1 dv, right? The antiderivative of 1 with respect to v is v, evaluated 0 to pi, which is 2 pi. Hold on, what? Oh, it was 2 pi. I was about to have a little miniature panic attack there. Okay, 2 pi. I was like, where's the 4? Shit. Okay, so that's going to plug in 0, so we just get 4 a squared pi, or 4 pi a squared. Check. So we just verified the surface area formula for a sphere. We've done that before. We actually did it. You could do this using, in Cal 2, revolving, like the first quadrant. Just take this first quadrant, that part of the circle, revolving it around the x-axis and using the surface area formula. But this is verifying it using a vector function to draw the surface. This is more powerful because this will work for more complicated surfaces. But it's nice that it verifies, right? All right, sometimes, we've got about 9 minutes left. Sometimes if we're lucky, all right, we can actually have a function, a surface, that's the good old-fashioned z equals f of x, y. The first type of function that we dealt with when we were drawing surfaces. You know, a good old-fashioned sheet of paper, the domain is on the ground, right? Not like a sphere where it wraps around itself. You can't look at z as being a function of x and y. If that's the case, all right, then you can basically let your u be x, let your v be y, all right? And then, so it's like this. In your vector curve, you're doing this is x, this is y, and then this is actually the function of x and y. So like if this were u and this were v, this would be some function of u and v. Then if you go through and do the cross product of the partials, it will always turn out to be this. Now I don't do it, I'm not going to do it. I say y here. Y, well, you would have to take this and take the partial with respect to x. What would the partial of this with respect to x be? 1, 0, partial of f with respect to x, right? What would the partial of this with respect to y be? 0, 1, partial of f with respect to y. Now if we cross these, lots of things are going to go away. We're going to get 1's in there. And then if you take the magnitude, square root of all that, you will get this formula. And it's super clean and quick and easy to use, all right? I'm going to give you an example of this. So it makes our surface area formula real easy to compute. So here's an example of that. We have, yeah, it looks bad. You have a surface, right? Find the surface area of the part of the paraboloid z equals y squared minus x squared, which lies between these two cylinders. It's hard to see it here. It's this orange looking thing. I'm going to pull all the other junk out of there. This is it right here. What we've done, though, is we've taken these cylinders and we've cut it. So it's like this sheet of paper that on one side it goes down, the other side it goes up, so there's like a saddle point in the middle. And what we've done is we've come in with two cylinders and chopped it, and then a smaller cylinder and chopped it. And we're looking at the surface in between those two. So we chopped it here from the top like this. And when we chop it, we just get that. And we want to know its surface area. So that's a pretty complicated looking question, right? Without anything that we have today, that would be a tough question. So when we look at it, say, okay, well, how do we draw this surface? How do we draw this surface? Well, it's here. This is the surface, right? We've got some restrictions, but that's basically the surface. So I know that the z there is a function of x and y. And that makes me happy because if z is strictly a function of x and y, then I know that the magnitude of the partial with respect to x crossed with the partial with respect to y should be equal to the square root of 1 plus, I'm going to write it this way, partial of f with respect to x squared plus partial of f with respect to y squared, which is the formula I gave you on the previous page. Now, for us, what would that be? I should have written what the function is. What is the function? Sorry. Y squared minus x squared. So this should just turn into square root of 1 plus 4x squared plus 4y squared, right? That's what the partials are. Well, the partial is what? Partial with respect to x is negative 2x, but then you square it, so 4x squared. Partial with respect to y is 2y, but then you square it, you get 4y squared, right? So that's what I would have to integrate. Isn't that a lot easier than having to do the partials, then the cross product, then the magnitude? Okay, it only works so if your surface is a function of two variables explicitly. All right, so let me get to where I want to set up the double. So I'm at this point right here. I'm trying to set up the double integral over some region D of this with respect to area. Now, I need to be able to come up with the appropriate restrictions on x and y so that I get just that part that got chopped off by the cylinders. How do you reckon we do that? Go to cylindrical coordinates or polar conversion. Right? Think about on that picture, on this picture, if I'm going to try and get restrictions on x and y, I need to look at it from the top and say, hey, what type of region is that on the ground? That's a polar region, isn't it? So I'm going to take this whole problem and convert it to a polar problem now. So what would my polar restrictions be to draw that thing? Remember, Do I have the, yeah, I have the cylinders up there. Can you tell me what the radii of those cylinders are? 1 and 3. So we want to restrict our x and our y into this region, so we switch to polar. So I'm going to let my r go between 1 and 3. I'm going to let my theta go between 0 and 2 pi. And now I just set it all up, right? This double integral. This doesn't matter, right? Because they're both constants. Square root of 1 plus 4r squared, right? Factor out a 4 from each of those two, and you're left with x squared plus y squared, which is r squared. So we have to see that to make our lives easier. You could replace that with r cosine theta, r sine theta, then do all the squaring in Pythagorean, but it's much cleaner if you just notice it. And then times r, yes, you cannot forget the mighty r that comes in every time you do polar. And that actually saves us a little bit, doesn't it? dr d theta. And then why did I do 1 to 1? I don't know. 1 to 1. And then at that point, you just go. I'll tell you what the answer is, okay? I don't have time to work this out. You should get at the end of this equals pi over 6 times 37 to the 3 halves minus 5 to the 3 halves, whatever that number is. That would be the surface area of that region between those two cylinders for that surface. Now, I had planned on working a few more problems here. I have not had a chance to get into the to do the homework solutions for this. All right, so I don't have the homework answers on video for these. But here's the homework assignment. I don't know when I'll be able to get those videos up. Hopefully in the next day or two. Maybe tomorrow morning if I'm lucky. So just, I know we're out of time, but just to give you an idea, we're done. We're done with 13.7, 6. 13.7 is probably going to take us all of next class and probably part of next week's class to get through 13.7. 13.7 is the last big, heavy section.